Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is inductive complex impedance. Our objective is to learn how to represent inductors as complex impedances for the purposes of AC circuit analysis. This lecture operates under the presumption the viewer has more than a passing familiarity with complex numbers and has watched the capacitive complex impedance lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. You are no doubt familiar with the DC response of resistors, capacitors, and inductors. In summary, resistors follow Ohm's law, a phenomenon that relates voltage, current, and resistance. Resistors dissipate all power supplied to them in the form of heat and are not energy storage devices. Even our initial discussions of resistors and sinusoidal AC sources demonstrated that resistors consistently follow Ohm's law and voltage and current are in phase with one another. Capacitors and inductors, in contrast, are reactive elements and can momentarily store and return energy. As such, the reactive nature of these energy storage devices need to be accounted for. Recall from our discussions about the time-variant DC response of capacitors that initially uncharged capacitors experience a current spike followed by rising voltage. This behavior can be summarized as current leading voltage for capacitive elements, and that the current spike occurs before rising voltage. The time constant established by the capacitive circuit under inspection determines how slow or fast this exchange of energy occurs. Similarly, recall from our discussion on the time-variant DC response of inductors that inductors with no established magnetic field experience a voltage spike followed by rising current. This behavior can be summarized as current lagging voltage for inductive elements, and that the current rise occurs only after the voltage spike. As with capacitors, the time constant established by the inductive circuit under inspection determines how slow or fast this exchange of energy occurs. For purposes of time-variant DC analysis, we never really explored beyond these horizons. If, however, we push the boundaries into circuits incorporating sinusoidal AC sources that continuously change, there is no initial nor steady state, and reactive elements like capacitors and inductors will continuously store and discharge energy on a cyclical basis. Despite this constant interchange, one truth remains constant. Current will be in phase with voltage for purely resistive elements. Current will continuously lead voltage for purely capacitive elements, and current will continuously lag voltage for inductive elements. We'll examine this phase-shifted response in greater detail in later lectures. The reactive nature of elements in AC circuit analysis are accounted for using one of two tools. One, either time-consuming calculus-based techniques, or two, simple algebraic techniques making use of complex numbers. My choice is to employ complex numbers. Bottom line up front, resistors, capacitors, and inductors can be represented as complex impedances, where impedance is a term quasi-equivalent to resistance for the purposes of DC circuit analysis. Only the complex nature of impedance includes time-shifted effects for purposes of AC circuit analysis. The true nature of complex impedance will only become apparent in later lectures. However, we at least need to learn to calculate complex impedance for now. Resistors, when represented as complex impedances, are elements entirely in the positive horizontal real x-plane. Frequency of the AC source has no effect on the magnitude of the resistive complex impedance. As such, a resistor, represented as a complex impedance, can be calculated as the resistance value at an angle of 0 when represented using polar format. When depicted in the impedance domain, resistors exist solely on the real horizontal x-axis, proportional to the resistor's magnitude. If you wanted to represent resistive complex impedance using rectangular format, it would be proportional to R, existing solely in the real horizontal x-axis, plus or minus j times 0. Since we're representing the complex impedance of resistors using a complex number, note the value ZR includes an overbar, indicating this isn't just a magnitude, but also includes a direction. Capacitors, in contrast, when represented as complex impedances, are elements that exist entirely in the negative vertical imaginary y-axis. Frequency of the AC source does have effect on the magnitude of capacitive impedance using the following formula. Z of C, note the overbar, equals 1 over 2 pi times the frequency in units of hertz times the capacitance in units of farads at an angle of negative 90 degrees when represented using polar format. When depicted in the impedance domain, capacitors exist solely in the negative imaginary vertical y-axis proportional to 1 over 2 pi fc. Finally, inductors, when represented as complex impedances, are elements that exist entirely in the positive vertical imaginary y-axis. Frequency of the AC source does have effect on the magnitude of inductive impedance using the following formula. Z of L, note the overbar, equals 2 pi times the frequency in units of hertz times the inductance in units of henries at an angle of positive 90 degrees when represented using polar format. When depicted in the impedance domain, inductors exist solely in the positive imaginary vertical y-axis proportional to 2 pi FL. Today we'll examine inductive complex impedance in detail. You'll note the units of complex impedance, regardless of the resistive, capacitive, or inductive nature of the element in question, are always expressed in units of ohms. Only direction gives some clue as to the resistive, capacitive, or inductive characteristics. Purely resistive elements have a magnitude in units of ohms proportional to R at an angle of 0. Purely capacitive elements have a magnitude in units of ohms proportional to 1 over 2 pi fc at an angle of negative 90 degrees. Purely inductive elements have a magnitude in units of ohms proportional to 2 pi FL at an angle of positive 90 degrees. Additionally, note capacitors and inductors are essentially mirror images of one another, with 180 degree differential between them, a fact we'll use to our advantage in industrial applications like power factor correction in later lectures. As an illustrated example of application of the inductive impedance formula, consider a 120 millihenry inductor subjected to sinusoidal AC with a frequency of 60 Hz. Let's calculate the complex impedance of this inductor, expressing our final answer using polar format. By all means, follow along and see if you obtain the same value as I do. By the way, this isn't a polite suggestion. Pause the lecture and try this on your own. If you're tracking, you should have obtained the following result. When we substitute our given values into the complex impedance formula for inductors, we arrive at an impedance value of 45.2 ohms at an angle of positive 90 degrees. When calculating inductive impedance, don't worry about the angle at first. Just calculate the magnitude using the formula 2 pi FL and stick at an angle of positive 90 degrees behind it and call it good. If we were to express this in polar format, Z of L would be equal to positive J, 45.2 ohms. Although this is kind of old-fashioned and all the cool kids nowadays are using polar format, as should you if you want to stay on the cool side of history. Introductory AC circuit analysis scenarios largely involve the use of this basic impedance formula. As such, let's gain some practice using it with some basic example problems. First problem. What happens to the complex impedance of this 120 millihenry inductor if I double the frequency to 120 Hz? No calculations, just think about it. Does the magnitude and direction of the respective complex impedance decrease, increase, or remain the same? Take the batteries out of your scientific calculator, put it on the table, and put your hands in the air. Just look at the formula and answer the question. What happens to the complex impedance of this 120 millihenry inductor if I double the frequency to 120 Hz? Does the magnitude and direction of the complex impedance decrease, increase, or remain the same? By all means, pause the lecture and think about this, but don't you dare touch your calculator because I'm watching you. If you have the level of mathematical competency I expect you to possess, you should realize that the magnitude of the complex impedance of the inductor should increase since the complex impedance of purely inductive elements is proportional to 2 pi FL. Given frequency is double, the magnitude of inductive impedance will be twice its original value. Angle, however, will remain fixed at positive 90 degrees. If we do the calculations, we find our hypothesis to be true. Substituting in the given values at 120 Hz, we find the magnitude of the inductive complex impedance has increased to roughly 90.5 ohms, double our earlier magnitude, yet the angle remains fixed at positive 90 degrees. Increasing frequency increased inductive complex impedance. I'll return to this point in a moment.